And the second talk of the session is Adam Shaw of Caltech, and he will tell us about using k-means to characterize a programmable analog quantum simulator. Please take it away.
Thanks. Thank you all for being here. It's nice to directly follow up Soonwon, who did a lot of the heavy lifting for me already, so we can get straight into some very interesting experimental results. I'm from the Andreas lab at Caltech. I'm talking about a couple of our recent results on benchmarking large-scale quantum systems, as well as using the fidelities which we learned from benchmarking in order to do noise learning to characterize analog as well as digital quantum systems. So just to give a very brief overview, what we're interested in is the generic entanglement challenge, where experimentally we always start with some simple initial state, some low entanglement state. We want to apply some quantum evolution, produce some highly entangled state for computation, simulation, etc. But the problem, of course, is in the modern day, we're always prone to errors. We can't even detect when these errors happen in sort of a normal quantum system. And so the generic challenge which we face is that we want to scale up these quantum systems, maintaining their control, minimizing their errors, and actually verifying that we've done the correct evolution. This question of verification is really at the heart of what I'll be talking about today. So with all that said, broadly, my talk will be broken into two different parts: benchmarking for large-scale analog quantum simulator, and then applications of those benchmarking type protocols besides just learning fidelities of operating some sort of quantum simulator. I am an experimentalist, and so I want to give a very brief overview of the experimental system which we're going to be using for people who are not aware. It's a so-called Rydberg atom array, which have been sort of coming into prominence in the last few years in the community. It's essentially based on the idea that if you have a series of tightly focused laser beams, you can trap a single atom in each laser beam focus. And then you can arrange these laser beams into roughly arbitrary arrays in 1 dimension, 2 dimension, or even 3 dimensions, create large-scale arrays. Our sister experiment at Caltech has around 6,100 atoms actually trapped in the largest scale experiment of this type. And you can then move these atoms around with fully programmable positions using atomic rearrangement techniques. Besides the optical tweezers, of course, we care a lot about the atoms which go into these optical tweezers. We use strontium atoms in our system. A lot of very interesting atomic physics to talk about these systems. I'm going to ignore almost all of that for now. All I'm really going to care about is that there's a couple of well-defined states for this atom. Basically, there's 2 low-lying energy states, which are both essentially metastable on the timescale of experimental type operations. And then there's this highly excited state, so-called Rydberg state, which is how we're going to be generating entanglement with these systems. So let's quickly go over how we actually generate that entanglement through Rydberg interactions. If you have an atom in the ground state, the electron will be sort of tightly confined around the nucleus. If you now excite that electron up to a very high-lying energy level, something like a principal quantum number of 100, the electron wave function will become quite large. And so now what we can think about is we can think about exciting 2 atoms that are some distance away from each other. And essentially the idea is if we have 2 atoms and they're separated far apart from each other, then both of them are able to be excited up to the Rydberg state at the same moment. If we bring 2 atoms and we bring them close together and we try to excite them up to the Rydberg state, we now find that basically their double excitation is blocked. The 2 electron wave functions interfere with each other, energetically penalize the state so that we don't actually create this doubly excited state of 2 atoms. All that really to say that if you bring 2 atoms close together and you turn on a global laser pulse, you create an entangled state between them in a very simple, experimentally straightforward procedure, where it's really just rearrange 2 atoms close, turn on a laser beam, and you get a Bell state out almost for free. This sort of operation of sort of generating entanglement in this way and controlling atoms and qubits in this way has been used a lot in recent years. Here's a very small selection of works across a wide range of disciplines which have been done with these systems. And really, even in the last few months, there have been even more exciting works which have come out a lot of different directions. The thing that's really important to note here is that these systems have been used both for quantum simulation, so sort of simulating complex dynamics cases, as well as quantum computation, so sort of digital quantum operations. And both of these are available with these atom array type systems. We've explored both a little bit with our system as well. It's relatively easy to see actually how these systems can accomplish both analog and digital type operations. I'm just simplifying again. We basically have this ground state, a metastable state, and the Rydberg state. Essentially 2 different ways you can define a qubit on this 3-level system. We can either have a digital qubit, which is this long-lived qubit here, which we can do gate-based operations and then sort of transiently excite up to the Rydberg state to do entangling operations. You could also define a qubit in this way here, and this is sort of what I'll call an analog qubit, where we sort of have this strongly interacting spin system. It realizes a Ising-like Hamiltonian, which we'll talk about a lot more in the rest of the talk. Most of this talk will be discussing this analog type qubit. I will briefly highlight that for this digital qubit, we sort of have record high gate fidelities around 997 with an error bar 4 there. And there's been a lot of work in just the last couple of months even on sort of realizing these high fidelity 2-qubit entangling operations across a wide range of different experiments. And really these Rydberg atom arrays have really started accelerating in their progress, both in terms of scale and control and high fidelity operations. That said, happy to talk about digital type operations, but for most of the talk, I'll be talking about our analog type operations, Like I said a moment ago, we can create analog, with the analog qubit, we can also create Bell states. We can actually do that with even a little bit higher fidelity of something like a little over 3/9 of fidelity for creating a Bell state for 2 atoms on this analog type qubit. And detailed error modeling of our system shows that something like 4/9 of fidelity is actually quite experimentally realistic. Of course, this is all for 2 qubit systems. And whenever we are actually thinking about doing real quantum computation or quantum simulation, we don't really care about what we can do with 2 qubit systems. We always care about these larger quantum systems and how we can actually use them to sort of realize important and non-trivial type dynamics. So that's going to be what most of my talk is on today. Before we get going, are there any questions just on the general experimental platform or anything like that so far before we just dive into the many bodies type stuff? So going on to the many body, the situation we're going to be considering for the rest of the talk is a one-dimensional array of something like up to 60 atoms. And the type of evolution which we're going to be considering is basically evolving these under a time-independent Ising-like Hamiltonian. The Hamiltonian being shown here, it's essentially just an Ising Hamiltonian with some long-range interaction. And the key characteristic of this Hamiltonian of these dynamics is that if you look at the half-chain entanglement entropy of these systems, what you basically find is that the entanglement grows with some system size independent rate before saturating at some system size dependent level as a function of time. We're sort of doing this infinite temperature dynamics that Soon-Won was mentioning a moment ago. Of course, this is not the state that we actually are able to produce in the experiment, because in the experiment we're always riddled with errors. And instead, the state we generically create is some noisy mixed state, which I'll call rho experimental. And just like Soon-Won was just talking about, the quantity that we care about is essentially the fidelity, the overlap between these two states, which is the probability that we don't make any errors experimentally. This is exponentially difficult to measure for large systems. Soon-Won already gave a nice introduction to how we actually go through this. I'll go through it one more time here. Essentially, we already know that we can basically estimate this fidelity via these linear cross-entropy ideas by measuring these bit strings in a single fixed basis and looking at this cross-correlation. And what, as Soon-Won said, what we've shown now is that we can actually also do this sort of operation for time-independent Hamiltonian systems. Just to give a very brief outline in a more sort of visual way for people to see what this really looks like, if we consider some time-independent Hamiltonian evolution, where we sort of think about starting all of our probability for a given quantum state on a single bit string, like the all-zero state, and then we apply some just generic Hamiltonian evolution, after some transient type dynamics, very quickly you see that this distribution approaches a very much random distribution, as Soon was talking about. And this distribution is basically this quantum fingerprint, which is very sensitive to the exact dynamics. And to show you what I mean by this, if we consider basically copying this state over, and now applying a single qubit phase flip error on just one qubit in the array, this error is initially does nothing toward this distribution because it's orthogonal to the measurement distribution. But even though there's this orthogonality, if we now just continue doing this evolution for a little bit longer under sort of natural Hamiltonian evolution, very quickly these two different distributions become basically completely distinguishable from each other. And then the fidelity estimator we use, this linear cross-entropy type estimator, is basically proportional to the correlation between these two. It's probably easiest if I just go straight on and show you that this does actually work for our system. So here I'm doing 2 different simulations of our system. One is a clean simulation where I'm not sort of doing any sort of error model type things. It's just pure Hamiltonian dynamics. And the other simulation, I'm using all of the pre-calibrated ab initio error model noise terms that we know about in our system to basically simulate what the experiment is probably seeing. And then from these, we can calculate both the fidelity and the fidelity estimator. And we can see that both as a function of system size and as a function of time, there's a very good agreement between these 2 quantities. And then, of course, we can put the experiment on this plot as well. And from the agreement between these 3 different quantities, we really do think that we can actually benchmark the experimental fidelity up to system sizes of something like 30. Of course, it's quite suspicious that I've ended this plot at 30, because inherent in what we're doing here is that we basically need to do these exact classical simulations of these types of dynamics in order to do this sort of cross-entropy type dynamics, or cross-entropy benchmarking, excuse me. And so the real question that we'll answer next is how do we extrapolate this for larger type systems? Are there any questions just so far on just this benchmarking, experimentally otherwise? Yes.
Yeah, perhaps can you say, I mean, without going into too much detail about, are you limited by shot-to-shot, different positions, or is it really decoherence from the given Rydberg states or so?
Yeah, I'll talk a lot about that in the latter half, so I'll pause there for now. The short answer is it's all lasers. It's almost always lasers for us. So it's non-Markovian noise sources for the most part. It's actually our killer noise source.
Yeah. Does it include any without measurement?
Sorry, say again?
Does it analysis include any without measurement error?
Yes, this includes readout. So this is not a true quantum fidelity because we do sort of include the measurement error. So it's sort of including that as part of this. That's why I say it's more like the probability that we don't make an error rather than a true quantum fidelity.
Yeah. Other questions? Yes.
So
So maybe I should have asked this someone, but so for the XEB, we know there's this phase transition in random circuits, like how well it estimates fidelity. Do you have any sense for what this would look like here?
Yeah, so we can sort of think about it in a very similar way. Basically, that same phase transition, we can think about basically as you get to too high of an error strength, your fidelity estimator basically breaks down. Without getting into too much details, maybe we can talk after. We know that we're well below that error threshold for these system sizes and for these one-dimensional arrays. So we don't think that we're at that threshold here, but if you sort of turn the noise up by orders of magnitude, then you do sort of see the same disagreement between the fidelity estimator and fidelity that you would see for these cross-entropy benchmark.
Yes, yeah.
Yeah. Great. Okay. So before going on to larger experimental systems, I want to very briefly make sure we're on the same page about what actually makes what actually makes classical simulation hard in the first place. We all sort of know that we can do exact classical simulation of quantum dynamics up to basically infinite time for small enough system sizes. There's another regime where we can also do exact classical simulation. It's by looking at the fact that because of the way that entanglement grows in these systems, if we look at some early time, whether there's 5 or 10 or 1,000 qubits in the system, there's the same amount of entanglement because there's sort of this constant entanglement growth rate. And this has been developed over many years now for sort of a whole wide range of so-called tensor network methods, for instance, matrix product states, which basically use this slow growth of entanglement to exactly simulate quantum states below some entanglement threshold. For instance, these MPS basically is characterized by a bond dimension chi. As long as the entanglement is below this bond dimension, the simulation is essentially exact. And then past this bond dimension, as the entanglement grows further, the simulation breaks down, and with this not exactly simulable regime at high system sizes and large evolution times. We can sort of redraw this phase diagram in a little bit more prettily with sort of classically exact regime, what I'll call it, and a classically approximate regime. And we can think about benchmarking the system in these two different regimes. We've already basically looked at the classically exact regime, but I'll show it again here for completeness. For instance, here's an n equals 27 size system. And for this size system, we can use a large enough bond dimension, something like 3,000, where we can exactly capture all of the entanglement growth of the system. So the entanglement growth calculated numerically is this black line, and then the bond dimension cap is this purple dashed line here. It's always greater than the entanglement, so that means that the classical fidelity is always 1, and then the quantum fidelity estimator decays largely exponentially, as you might expect. Something changes now if we go into the classically approximate regime. Now, as soon as the entanglement passes this dashed line, this bond dimension cap, now the classical simulation fidelity breaks down and starts decaying precipitously. And at the same time, the benchmarked quantum fidelity also breaks down and no longer represents what we think of as the true fidelity. And this is not that surprising because in some sense, the fidelity estimate that we're using is this cross-correlation between both experiment and theory. So it's inheriting the errors from both the experimental true fidelity and also the simulation fidelity, which are sort of orthogonal to each other in some sense. And then if we go to large enough systems, we can't actually go to a high enough bond dimension to really ever be able to benchmark these systems. And of course, this is the whole point of sort of doing quantum computation in the first place. So there are a number of different ways to try and get around this problem. In particular, for instance, for like the Google supremacy type experiments, there are essentially system size type extrapolations, a little bit more subtle than that for sure, but essentially system size extrapolation via these so-called patch or elided circuits to be able to extrapolate into this large entanglement regime. For our analog quantum simulator, these methods explicitly do not work exactly because of those non-Markovian noise sources that I talked about earlier, and I'll come back to on the next slide. And so we really had to think about a new method of trying to break into this new regime. And the way that we think about doing this is by looking at the fact that if we use too small of a bond dimension to benchmark a system, then this benchmarked fidelity will break down and will sort of go too low. But if I now use a large enough bond dimension, it will give me the correct answer. And so there's some transition between using too small of a bond dimension and getting the wrong answer, and having a large enough bond dimension to fully capture the entanglement and getting the correct answer for the fidelity. And so what we can actually think about doing is essentially extrapolating these fidelity estimators as a function of the classical resources, these MPS bond dimensions being used in the classical simulation. So just to be very concrete, what we do is we basically run our experiment for many different system sizes and many different evolution times, and then we benchmark it with many different MPS simulations of different entanglement, of different bond dimensions, different entanglement caps. And then for each of those, we can basically plot what that fidelity estimator looks like as a function of bond dimension. For small enough system sizes, this value increases, and then saturates once the entanglement is fully captured in the system. For the large system sizes, it does not saturate because we haven't reached a large enough bond dimension, but we can extrapolate as a function of bond dimension, basically find what we estimate as the actual fidelity. So it's very much an extrapolation type technique. I want to be clear about that. but we've done extensive numerical cross-checks to sort of make sure that our method works, and I'll go into a little bit more on the next slide here. All that said, so here I'm going to show some of the data, and then we'll go through some of it. So here, the markers are trustworthy data points where we can sort of do exact classical simulations for system sizes of 24, 42, and 60. And then the green line and fill is this sort of resource extrapolation, which is really extrapolation over system size, time, and resource. And what you can immediately see is there's some very odd behavior. Because for the n equals 24, we have something that looks largely exponential. N equals 42, you start seeing some amount of bending of the fidelity estimate down here. And if n equals 60, this actually looks quite bent and non-exponential. And I'll say that I spent a lot of the time in my PhD trying to figure out what was wrong with this plot here. And no matter how I did this resource extrapolation, or even different methods of doing this extrapolation, not this whole bond dimension thing, but other methods as well, basically this behavior always showed up in this exact same way. And so at a certain point, started trying to figure out not what the bug in the code was to a certain extent, but what the actual physics was that's going on here. And once we sort of started looking into this much more detail, what we actually realized is that our dominant error source in our system, which is these non-Markovian laser fluctuation noise, basically our laser fluctuates in intensity from shot to shot, this actually gives rise to a power law type fidelity decay, which shows exactly this type of bending behavior, which for large fidelities looks largely exponential, and then once you get down to small fidelities, starts bending. And we had never seen this behavior before because when we were studying small system sizes, we had never reached these low fidelities of something like 20%, so we had never actually seen this. Of course, then after we sort of discovered this and sort of analytically came up with these type descriptions for how these noise sources should look, we can then look back at our error model, and we can see that the error model shows basically the exact same behavior as we see for these large system size data. And we can actually extrapolate from the small system size error model to the large system size experiment and see that they're relatively consistent. Yes?
Significant if you have low fidelities?
No, sorry. I just mean that it looks, if you just look up to like something like 30% fidelity, and you just look at it by eye as a grad student, you think that looks largely exponential. And you don't really see the sort of non-exponential tail of it until you get to these low fidelities where it really starts diverging quite a lot. So that's what I mean by we didn't see it. It's literally that we thought that it looked exponential because it was fitting well to an exponential in that fidelity regime. You have to go to a larger scale to be able to see this. And it's somehow, it is sort of scale invariant that this always shows up at these low fidelities, whether the system size is large or small. And because we were reaching these small fidelities for these large system sizes, that's where we really saw this bending quite significantly. And I'll say that besides this sort of shot-to-shot intensity noise, we've since have sort of done the same theory calculation for several other types of noise sources in our system. And basically every type of non-Markovian noise source in our system gives some sort of power law behavior that looks like this rather than this exponential.
So the parallel decay is like a better fidelity?
Yeah, people always ask this. So it is better only in the sense that, you know, what are we actually doing here? If I take my Hamiltonian and I take any Hamiltonian miscalibration, then the fidelity will actually decay sort of quadratically. It will decay worse than exponentially. So it'll be quadratic. What I'm doing here is that my laser has some Gaussian distribution of intensities, for instance. And because for a Gaussian, there are more parameter choices that are close to correct than there are parameter choices which are far from correct. When I average over that Gaussian, the average of all of these sort of quadratic decays looks like this power law, which looks better than exponential. So any actual miscalibration is worse than exponential, but when you average over these Gaussian choices, that's when it gives this power law. Any other questions about this? Yeah.
Does it mean that experimentally there is no like some random noise happening through the time evolution?
So we also have Markovian noise sources like atomic decay that can happen, like sort of an amplitude damping channel essentially, which stochastically happens in our system. Really for this analog type simulators, and really probably digital quantum processors as well, there's a mix of Markovian and non-Markovian noise sources, stochastic and quasi-static noises, which are constantly affecting you. That's one of the main challenges of benchmarking these systems.
Isn't like the stochastic noise always kind of upper bound is fidelity decreased by the exponential?
That's right. So there's also some exponential sort of envelope on top of this thing. You're sort of seeing the mixture of an exponential and these power law decays all sort of mixed together in this. Yeah. And when I say that we extrapolate our error model, I mean that sort of extrapolating all those different error sources independently, sort of looking at this sort of mixture, that's where we see consistency with the experiment between small system size error model and large experiment.
The noise you were modeling there was the laser intensity from shot to shot, right?
Exactly, yeah, or really any sort of Hamiltonian parameter miscalibration shot to shot, quasi-static. Yes.
And you think it's coming from the laser?
It's almost certainly coming from the laser. It sort of matches you can sort of back out from this. You can go in the reverse and figure out how much standard deviation you expect. And it matches almost exactly with the ab initio calibration of the laser intensity fluctuations. But there are also fluctuations that are shot to shot, like the atomic position fluctuations are a little bit varying shot to shot. Those are also quasi-static. And we can't get into the fine details of that because the laser noise sort of over encompasses them, but those will also give the same behavior. Okay. So all that to say that with this sort of cross-checks, and there are many more that I can go into, we really do trust that we're able to sort of get an estimate of the actual fidelity of these large system sizes. I'll mention that this resource extrapolation technique we think should be actually quite scalable up to something like a few hundreds of atoms, though of course we haven't tested that experimentally, so can't say for sure. But for at least up to system sizes of 60, we find a fidelity of something like 10% to create a state with maximum entanglement entropy using this analog quantum simulator. And it's hard to sort of think about many-body fidelities and think about what this actually means. I'll give 3 different points of view. One, the sort of simplest and stupidest is just that this is quite a bit larger than 1 over the Hilbert space dimension for the system. We're sort of picking out one state with a pretty good probability compared to just picking a random state. I'll say this is consistent with our 2-qubit fidelity of 3 nines. And last thing I'll say, and I'll preface it by saying this is not a fair comparison because Sergio's in the room, is that when you look at the Google quantum supremacy experiment from 2019, there the fidelity that was reached for something like 53 qubits is about an order of magnitude lower. There's obvious differences in terms of this being an analog quantum simulator versus that being a digital quantum processor with higher level of control. But it sort of goes to show that when we use these analog quantum simulators, we can target specific applications and still achieve very high fidelities for accomplishing those tasks, which might be quite impactful in the near term for quantum computation and quantum simulation type purposes.
I think that's fair.
All right, he says it's fair. Good. Okay. Going forward then, so we have this value here of something like 10% fidelity. What does this mean in terms of classical simulation? I'll quickly go through this. We can sort of think about what actually better represents the quantum world. Is it our experiment here or some MPS simulation of our experiment? We can basically look at the minimum classical resources needed to simulate our experiment. We can look at this as a function of system size, and we find a system size 60. We have something like 3,500 as the Bond dimension. In terms of actual simulation time, because this is a one-dimensional system, these tensor network methods are very good. And so this, with a very highly optimized, actually novel algorithm, this takes about 180 core days on a Caltech supercomputer. Obviously not advantaged, but the point here is that if we then look at how this time scales as a function of this equivalent 2-qubit fidelity, right now for our value of around 3 nines, this is 180 core days. As you increase this marginally, and I told you before that really we think 4 nines of fidelity is quite realistic, this goes from 180 days to 100 years and very quickly approaches the age of the universe. So really, the quantum experiment is not sitting still. It's very much improving at a very actually rapid rate. And so when we think about sort of the state of the art in looking at how entanglement and how large scale entangled states are created, the Sycamore experiment, this was basically a 2-dimensional random unitary circuit designed to be as explicitly complicated as possible. Whereas what we're doing here is basically time-independent global one-dimensional evolution. It's the simplest and most natural type of quantum evolution you can imagine, and yet still we're finding classical computers struggle to keep up. And there's interesting physics that's actually being discovered along the way, as Sunon was just mentioning a moment ago. With all that said, we sort of have a fidelity, we'd be able to benchmark our system. And now what I really want to talk about is that there's a number of different types of applications we should go into. And I'm not going to be able to go into all of these during this talk. I'll sort of pick out a couple of them that I think are most interesting. But before we go there, are there any questions? Just start on any of the benchmarking stuff we just had before. Can I ask how much time I have, by the way? The time? Okay, great, perfect. Okay, so I'm not going to go through all these. I'm actually going to pick out first. I'm going to talk about this entanglement estimation type idea. So essentially, when I just made that ad hoc comparison to the Sycamore experiment a moment ago, there we have these ideas of, okay, well, one experiment got this fidelity, one experiment got this fidelity, and it's hard to really sort of compare them on an apples-to-apples basis. Is there a metric that we can come up with which is a more fair comparison between different types of experiments, both those that are sort of doing digital type operations as well as analog type operations? And the thing I want to think about is that whenever we've talked about entanglement in this talk so far, we've talked about pure state entanglement, some entanglement of a pure state that we are trying to produce. But of course, what we actually get in the experiment is this noisy mixed state that we've been talking about. And so what we want to know is what is the actual experimental mixed state entanglement content that the actual experiment actually produces. And this idea is actually notoriously hard to measure or even think about even theoretically. Digging through a lot of old literature and skipping over a lot of details, we basically come up with a very simple proxy of the actual mixed state entanglement, which is given by the pure state entanglement. For experts, this is a negativity, to be clear. This is the pure state entanglement, which we can basically extrapolate or estimate via ulterior methods, plus the log of the fidelity. And then the fidelity will be less than 1. So this number here will be negative. And so this mixed state entanglement will be less than the pure state entanglement. You can actually prove that this is exact for certain states, for instance, isotropic states, which are a mixture of maximally mixed states and maximally entangled states. And then we can actually prove that this is a provably tight lower bound for instance, random unitary circuits, as well as for the sort of ergodic Hamiltonian type systems that we study in our experiment. For instance, here we're basically plotting the mixed state entanglement proxy as a function of time and system size for our experiment up to system sizes of n equals 60. And why do we care about this? We don't really care about this just because we can look at our entanglement for our system, but because this formula here applies to any sort of quantum simulator, which is essentially for which you are able to measure a fidelity for doing some sort of quantum operation. And so what we can do is we can actually make a plot, basically, for instance, here is a function of system size, where we look at the maximally entangled mixed state entanglement for many different types of experiments, both sort of digital quantum processors as well as analog quantum simulators, and really compare them head to head on the same plot in terms of their ability to create these large-scale entangled states. And we can then sort of use that as a proxy, sort of in a quantum volume type-esque way, for how these systems are able to do these complicated tasks. This is general purpose, includes both qubit quantity and quality. And last thing I'll mention here is that while we're not sort of fully defined on some of, well, okay, I'll say first, this quantity, this negativity, this mixed state entanglement we're looking at is very closely related to, for instance, how many Bell pairs could you possibly extract from the system. So this is a very physically real number in some sense. It's literally saying, how much entanglement could I get out of my system if I had perfect LOCC type operations. And then we think that there is a good correspondence between this quantity here and sort of the actual classical simulation complexity of these type of operations as well. So that's a little bit less defined at the moment. We're still trying to work on it a bit. All that to say that we think that we actually have this method of comparing all these different types of experiments on one plot, which we think is quite exciting to sort of bring the analog quantum simulators into this comparison with digital quantum processors. Any questions on entanglement estimation, mixed state entanglement, anything like that?
I think this awareness measure is, I agree, is quite related to simulation complexity. I think the difference is when you look at simulation complexity, eventually you care about memory.
Right.
That makes sense.
Right, yeah. Sergio has mentioned this to me before. I should have said yes, that yes, this doesn't include the sort of memory cost that you would run into, of course, if you sort of try to simulate a large scale system. But in terms of sort of the processor number of essentially the bond dimension that you would need to simulate something, sans memory. Okay, great. So this is sort of a nice measure that we think is actually quite applicable to many different types of systems, and we hope will be used by other types of analog quantum simulators and digital as well. But for the last little part of the talk here, I'm going to transition into some more recent work that we've done on basically, after we've measured these fidelities, it's nice because we can say we have a fidelity of 10%. What is it actually good for improving our systems? Now we're going to be talking about noise learning. I'll highlight that a lot of the theory done here was done by Daniel Mark, as well as in a collaboration with Soonwon. And really, all of this has been in collaboration with them throughout the whole time. So what do I mean by noise learning? We're going to step back from the Hamiltonian systems for a moment and just consider RUC evolution, some n qubits in depth d. And as we just heard about in the last talk, you can basically measure this, measure the output of this RUC system, and you'll get some probability distribution. And if you look at the probability of probabilities of this, then you'll see that this sort of follows this universal distribution, well known to be this exponential distribution or Porter-Thomas distribution. And then the key thing here is that if I introduce just a single error in this array, so I just put a single error somewhere, and I assume that my RUC is scrambling enough for some hand-wavy definition of scrambling enough, then I'll get some different distribution out. But the actual probability of probabilities from which it is drawn will still be a Porter-Thomas exponential distribution. This is really the key thing. We're not really thinking about these probability distributions. We're really thinking about these probability of probability distributions, what I'll be talking about next. And you kind of redraw this in a different way and say that with some probability f, which is the fidelity, no error will occur in our RUC circuit, and we will sample from a certain probability of probabilities, certain POP distribution. With a probability of 1 minus f, that error will occur, and then we will be sampling from an independent exponential distribution. And now I can think about not just having a single error in my system, but now having something like the space-time volume number of errors in my system. And now for each of those different possible errors, or really combination of errors, I get a different independent exponential distribution. And when we look at the total aggregate sum of our quantum device, our quantum processor or simulator, we're not actually keeping track of all these microscopic errors. We can't. That's the real problem that we're trying to solve here. And so the distribution which we measure at the end is the incoherent sum over all of these if independent distributions. And if we take all these independent distributions of exponentials, you can sort of go through and you get something called a hypoexponential distribution, which is basically a convolution of multiple exponentials with different weights. The exact mathematics isn't too important. The key thing to note here is this hypoexponential distribution is entirely characterized by the noise channel that we decided upon. For instance, here we decided that we would have a local noise channel with single qubit Pauli errors, and by the fidelity, which we can measure experimentally. Okay? The take-home message here is that by just given some analytically decided upon noise channel and that measured fidelity, we can always write down what this distribution should be and compare it against experimental distribution. Yes?
Does this depend on the type of noise? Like, should the noise be depolarizing or something?
No, that's actually really the key thing. I'll get into that in the next slide, but this is very generic in the sense that what this method is essentially counting is any different type of noise, whether it be Markovian, non-Markovian, unidal, non-unidal, doesn't matter, as long as it can be scrambled back into an exponential distribution, this sort of takes care of it. Okay. Let me go on to the next slide and sort of show you the result, and then we can talk a little bit more about it. What I'm doing here is random unitary circuits. I'm still focusing on RUCs for now. And what I'm doing in each different case is I'm doing 4 different instances. In each instance, I'm taking an RUC, and I'm simulating it under a given noise model. Okay? And then I'm taking that probability of probability distributions that you get out, and I'm plotting it as the bars here. So basically the bars, which looks like a fill on this display, is basically the numerical values we get out given these different noise channels. For these different noise channels, they're basically characterized just by a weight distribution, which we can write down. We have, it's very easy to write down these weight distributions, actually. You can see that here we have these global Gaussian coherent errors, which are like these laser intensity errors. We have global depolarization, independent local Pauli errors, amplitude damping errors, etc., mixtures of both of them. And what you see in general is that in all cases, the fill, the bars, are in great agreement with the analytical prediction for that noise channel, which are the thick solid lines, while being clearly visually distinct from the predictions from the other noise channels, which are the faint lines. And then I can then say that you don't only have this for RUCs, but you can also do this for Hamiltonian systems. Here's simulation, for instance, of a mixed field Ising model type system. The key thing to note here is that why does this actually work for Hamiltonian systems? This basically goes back to what Sunwon was talking about in the last talk, that a lot of the work that we've done over the last few years is doing a lot of extensive theory work to basically show that most of the statements that you can make about RUC type systems, you can also make about these ergodic analog quantum simulator systems implementing time-independent Hamiltonian dynamics. And so I think that if I sort of zoom out to what I think is most important about this type of a work in terms of the comparison between digital and analog, it's that we're really trying to bring the suite of understanding that we have about these digital RUC type systems, which has been developed over a number of years, to bear on these analog type systems, which I think is going to be a really fruitful research direction. Of course, then we can do this and apply this to experimental data. For the experimental data, it's essentially mollified a bit by finite sampling. In reality, you don't actually want to look at the full probability of probabilities. You want to look at low order moments, which I can talk about, which provides the same predictive power. But even looking at the full probability of probabilities still actually gives you the correct answer. I'll just show here that because of finite sampling, these distributions basically get sort of smoothed out. But you can sort of analytically predict this. You can actually invert it, but here we're not doing that. But basically here, I'm showing experimental data as the gray bars. And then for a couple of different noise models, including our ab initio sort of full air model noise model, I'm plotting the analytically predicted probability of probabilities distributions. You can sort of see visually already that maybe the full air model shows the best agreement. We can define some distance, which is like a chi-squared distance between different distributions. And then we can look at which one of these different distributions actually shows the best agreement. We see the full air model does the best here. But then the really key thing is that what we can essentially do is just come up with tailored and designed weights for these hypoexponential distributions that correspond to any sort of noise model we can think of. For instance, what we can do here is look at some noise model where we vary the fraction of coherent error in a mixture between local Pauli errors and global coherent errors. And what you can see there is that this sort of black line here basically shows this same distance to experiment, and we see that this has a minimum at a certain point. The key thing is that we can then do this, for instance, for RUC simulation, and we can really show actually that the actual noise parameter, for instance, this like coherent error parameter that we had in the numerics, is well approximated and well found by doing this type of analysis, by just looking at these sort of distances between POP distributions. With all that said, I'm pretty sure that's the end of my talk here. I think that the point overall is that the quantitative benchmarking, which we're doing here, sort of started out as a way to just understand how well we were controlling these systems. But at the same time, it's improving our ability to perform quantum science. It's realizing new science applications in terms of this emergent randomness that someone was talking about. And by measuring these fidelities and by sort of characterizing these systems, we can actually learn about the microscopic behavior that's sort of underlying them. And that's what I think the major take home here is, and that these analog quantum simulators, I think, are really a very fruitful platform to be able to study a lot of interesting near-term and far-term quantum science. So with that, any more questions? Thank you. And of course, thank you to my collaborators.
Hi. You mentioned that you have a novel simulation method that does better than the MPS with just huge one dimensions. Is that right?
That's right. It's essentially something that's finely tailored for the Rydberg type dynamics, these sort of one-dimensional chains with long-range interactions. It basically takes advantage of the fact that sort of entanglement grows and has this light cone structure to basically truncate the MPS in a clever way that accounts for this light cone. We can talk about it offline if you want, but yeah, it's very well suited for these one-dimensional long-range type systems. And actually, if you just look at sort of a standard TBD type MPS simulation on the same plot, it would basically like go straight up almost. So we really had to develop this new method to do this simulation.
Okay, sure. Yeah, let's talk about it.
Yeah, just a small question. I'm curious. Your mixed state entanglement proxy, is that kind of bounded by like mixed state entanglement measures in one way or the other? Can you kind of make this precise?
Where is it? Here it is. So this actual value that we're looking at here is a negativity, which is sort of an upper bound for the distillable entanglement in the system. And so what we can show is that this value here, we can prove it's a very tight lower bound for realistic experimental systems. Yeah, so it's a provably tight lower bound.
Okay,
that's right.
Any more questions?
And I'll say that besides being provably a tight lower bound, we can of course do error model simulation of our system, which is realistic, and we see that it's an extremely good, very, very tight lower bound in general.
So these new MPS method you guys have, can you extend it to 2D or is it purely 1D?
Yeah, we are working on that for sure. It's a little bit hard because sort of the plaquette size that you sort of need to encompass these long-range interactions grows quadratically then when you go to 2D. And so the real benefit that you get in the 1D system is that you can basically truncate your evolution of 60 atom systems to a bunch of like smaller like 6 atom systems to account for the long-range interaction. We are working on ways to extend it, but it's not naively clear how to do it. But I think it's probably possible just with a lot of work.
Any last question?
And of course, you still have sort of connectivity problems of how to truncate correctly in 2D that it doesn't really solve in some sense.
Last question.
Okay, good. Let's thank Adam again for the nice talk. And we'll meet again after lunch at 2 p.m.